Namaskar and welcome back to this lecture on concrete engineering and technology, where we are revising fundamentals of concrete, doing proportions of concrete mixes, concrete construction, special concretes, mechanisms of deterioration in concrete, reinforcement of concrete structures and their maintenance, basically the kind of things which all civil engineers do, and we are trying to see how the perspectives have changed in the last couple of years, maybe 10 years, 20 years, and we want to study or learn a little bit more about the latest developments in this area. Now, continuing with our discussion on the reinforcement of concrete structures or the reinforcement used therein, we were trying to address the problem of reinforcement corrosion, and we had said that basically there are three approaches that we can adopt. One is to coat the bar, the other was to use non-corrosive reinforcement or to prevent the corrosion electrochemically. As far as coating the bar is concerned, epoxy coated bars or galvanized bars was the option. As far as non-corrosive reinforcement is concerned, using continuous fiber, using CFRM or continuous fiber reinforced material, which has basically long fibers embedded in a matrix, that is the option. And as far as electrochemical prevention is concerned, we could use cathodic protection. Now, in the last discussion, we were trying to address the issue using CFRM. So, we will continue from that point onwards, and these are the pictures that we have seen. This is the different fibers, carbon, glass, aramid in the raw form, that is the fibers themselves, which are extremely fine. And then we had seen this picture, which is the products from the long fibers, and we can see that they are in the form of rods, strips, two-dimensional, three-dimensional, woven into nets, fabrics, and so on and so forth. Now, continuing our discussion, let us try to understand a little bit more about the structural behavior. Let us try to understand the structural behavior of CFRM. We will try to study it using the stress strain curve as the manifestation. We will try to see how the stress strain curve of CFRM goes or behaves as we use different fibers, as we use different fiber volumes, and so on. We had talked about the fact that a CFRM can be looked upon as fiber embedded in matrix, and the properties of this CFRM could be varied by varying the type of fiber or its content, that is the volume of the fiber in the matrix. And what we will try to do is to study the stress strain curve of this CFRM in case when the load is parallel to the orientation of the fibers, that is the longitudinal application of load, and when the load is transverse to the orientation of fibers, and that is the transverse orientation of load. Now, as far as the unidirectional CFRM, and that is what we are really bothered about, is concerned in the longitudinal loading, for a CFRM loaded along its fiber axis, the strain in the fibers in the matrix is the same. What we are saying is that if we take a CFRM, which is like this with a lot of fibers, and we apply the load in this direction, then the strain that we see here, whether it is in the fiber or it is in the matrix, it is the same, and that is the value that we have for the composite itself. And under those conditions, if we apply simple rules of stress and strain, we will get the equations which are given here, that is ECL will be equal to EM times VM plus EF times VF, which can be written as, because the volume of the matrix is nothing but 1 minus the volume fraction of the fiber, as 1 minus V f plus E f times V f. So, different modifications or different adaptations of this equation can be used depending on what we are really trying to determine. Here ECL is the modulus of the composite in the longitudinal direction, and the M and F are the subscripts which are used for the matrix and the fiber. So, naturally we can see that the property as far as the composite is concerned in the longitudinal direction is a function of the properties of the fiber and the matrix, that is the E of the matrix and E of the fiber, and the volume fraction of the matrix and the fiber. So, if we want a certain E, we can get it by varying the E m or the E f or by varying the V f. So, this is something which we must keep at the back of our mind when we are trying to study applications of CFRM as far as civil engineering or concrete construction is concerned. Similarly, if the load was applied in the transverse direction, that is in a direction perpendicular to the orientation of fibers, we are not doing the derivation here, but the E transverse. So, this T here is transverse. So, the E transverse of the composite can be written in terms of V m upon E m plus V f upon E f, and we can write V m as 1 minus V f like we had done in the previous case. Now, if we translate that into a stress strain curve, this is what we get. The sigma c, which is the stress carried by the composite, can be written as sigma f times V f plus sigma m times 1 minus V f, which means that the total stress that is carried by the composite is equal to some fraction, that is composite, some fraction of the stress carried by the composite is carried by the fibers, which is equal to sigma f times the volume of the fraction or the volume fraction of the fibers, plus some fraction carried by the matrix, which is sigma m times 1 minus V f. Graphically, if this is the stress strain curve of the matrix material alone, and this is the stress strain curve of the fiber alone, then depending on the volume fraction that we have, we will get the stress strain curve of the composite to be somewhere in between, and where it lies between these two lines would depend on the volume fraction. And therefore, this and this are critical points as far as we are concerned for a given strain value. Now, if we translate our understanding of the stress strain behavior of the composite to a graph which says or which shows us the variation of the E of the composite versus the volume fraction of the fibers. If this varies from 0 to 1, as far as the composite is concerned in the longitudinal direction, the variation is linear, as we have seen, whereas in the transverse direction it is not linear and it follows this graph. So, we must keep in mind that the modulus of elasticity as far as the composite is concerned is related to both the modulus of elasticity of the matrix and the modulus of elasticity of the fiber, and is determined by the volume fraction and also whether the fiber is loaded in the longitudinal direction or it is loaded in the transverse direction. Obviously, in a situation where we are talking of bidirectional or multidirectional fibers, where the fibers are oriented in both directions or in random directions, we have to have this understanding at the back of our mind when we formulate the derivations for those cases. When it comes to load sharing between the fibers in the matrix, this is the formulation that I have shown to you for the longitudinal loading, that is the loading which is along the direction of fibers. So, we can see that the strain in the composite has been taken to be the same for the fiber and the matrix, and if this is the condition, then we can write it as shown here in this box, that is sigma c by E c is equal to sigma f by E f is equal to sigma m by E m. Now, if we take these first two terms, or if we take these two terms, then we get this equations here, and if we take these two things here, we get these two here, and we can derive the kind of equations which are given at the bottom. Once we clearly understand what these equations carry, we can simply carry out a simulation or just put the numbers, and we will find that the percentage of load carried by the fibers as far as the total load carried by the composite is concerned, depending on the volume fraction and the ratio of the E of the fiber and the E of the matrix, could be something like this. So, depending on how stiff the fiber is compared to the matrix, the load carried by the fiber will be different, and as the fiber becomes stiffer, it carries more load. That is something which we must carry home from this picture. Now, this table here is just a data sheet which tells you that depending on the type of the fiber, which is glass or graphite or boron or silica, tungsten and Kevlar, how is the tensile modulus, the tensile strength, density, how do they change? So, we cannot go into the details of these numbers, but what we have to see is how do these numbers compare with conventional materials such as steel or aluminum or glass. So, if we see for steel, for example, the density is 7.8 and the modulus of elasticity is 210 GPa. Now, compared to these two, if we look at e-glass, the density is just 2.54 and the modulus of elasticity is 72. So, this fiber is approximately 1/3 as far as density is concerned, and is also about 1/3 as far as the modulus of elasticity is concerned when we compare the performance of e-glass with steel. Steel being the conventional reinforcement and e-glass being a non-corrosive alternative, which we are considering for application in structures where corrosion could be a severe problem. Another way of looking at some of this information is to talk in terms of a specific modulus or a specific strength. Now, specific modulus and specific strength is these modulus values divided by the density. So, we try to say that what is the specific strength? That means, for every kg of material that we use in the structure, what is the strength that we get? So, if we look at those values, we find that the fibers are performing much better, because their tensile strengths are much higher. If we look at steel, for example, it is 3.5 versus 0.34. For graphite, it is 2.1 versus 0.14 and so on. The specific strengths are much higher, and so is the specific modulus. Continuing from the discussion of bulk materials, which was that kind of data which was shown in the last table, we have properties of structural materials and bidirectional fibers. If we look at the similar numbers here, we can draw our own conclusions, that if whether we use glass with epoxy, Kevlar with epoxy, carbon fiber with epoxy or boron with epoxy, because we must understand that epoxy is also a very important component of the composite and contributes to its structural performance in terms of load carrying capacity, in terms of the modulus of elasticity and so on. And we get these numbers here for the fiber composites as compared to these numbers here, which is for steel and aluminum here. So, we have these are the numbers for fibers and these are the numbers for conventional materials such as steel and aluminum, except that of course, aluminum is not very much used as far as reinforcement is concerned, and we are really bothered about steel versus fiber comparisons most of the time. Now, let us try to study or look at the tests for quality of CFRM. It is not only the tensile properties that we are bothered about, we also need to look at flexural tensile properties, tensile fatigue properties, creep, long term relaxation, coefficient of thermal expansion, performance in anchorage and couples, alkali resistance, bond resistance and shear properties and so on, if we really want to apply a CFRM such as this as far as reinforcement in concrete structures is concerned. For that, we need to look at once again on the basic behavior of reinforced concrete. Now, this picture here shows a very simple beam which is loaded in the center, simply supported beam loaded at the center, which deforms like this, and this here is the reinforcement, because concrete is weak in tension, and unless we have this reinforcement here, these cracks are likely to run through and destroy the beam. So, once we have this reinforcement, the cracks do not run through and these materials go in tension, and that is what the basic behavior of reinforced concrete is all about. So, as far as we are concerned, we understand this behavior pretty clearly. We understand the stress strain behavior of concrete, we understand the stress strain behavior of mild steel and high steel and high yield stress deform bars. So, as far as civil engineers are concerned, we are familiar with this graph. We know how concrete behaves as far as stress strain is concerned. We know how mild steel behaves with this plateau and along yield region in the strain, which allows this mild steel to deform, and how the HYSD bars behave, where there is no well defined yield point, but still we have a reasonable amount of deformation after the first yielding that occurs here. Now, we understand this as far as this reinforced concrete beam is concerned. Our challenge now is to translate this understanding when we are using FRP materials or FRP as a reinforcing material. This material is characterized by a higher strength here as far as the failure stress is concerned, but a lower E. So, it is characterized by high strength, it is characterized by a low E, and it is characterized by brittle failure. That is, it does not have this region of large deformations being possible. So, with this understanding, we have to apply FRP as far as a reinforcing material in concrete construction is concerned. Now, before we apply FRPs in concrete construction, we must also now understand what are the different tests that need to be carried out in terms of fatigue, in terms of creep, relaxation and so on, bond, and then try to study the applications in concrete. This picture here shows the tensile tests on FRP bars. So, if we look at the tensile test, this is how the FRP bar fails. So, it is a very brittle failure, destructive in nature, and does not give us any time as far as the necking is concerned. So, there is absolutely no large deformation region. Another thing which we will see later on in the next slide perhaps, this slide here shows the failure of the common CFRM, the aramid fibers, the carbon fibers, the glass fibers, and in all cases we see that there is a fair amount of delamination that has occurred, fibers have become separated from the matrix has completely collapsed, and so on. One thing I would like to point out when testing CFRM is the role of these anchors at the end of the specimens, this part here. The region that goes into the machine where the FRP sample is held and the load is applied. One of the major challenges in testing and using FRPs is the development of appropriate devices to hold them in position while the load is applied. The problem is mostly encountered when the testing is carried out in the laboratory or when they are used in pre-stress concrete construction. You know that in post-tensioned pre-stress concrete, the fibers or the reinforcing tendon is to be held in position over a long period of time using a device which will anchor the tendon. And this is more or less similar to the device that holds the tendon in position or a specimen in position when it is tested in the laboratory. The problem arises from the fact that the teeth in the jaws of a normal chuck could easily cut through the FRPs even before the tensile strength is reached. An FRP rod, when it is held inside the chuck and we want that only this portion should be pulled or the load should be applied, how do we hold this in position? One of the ways to do it is to have some kind of teeth which will grip this specimen. Now, if this material here, which is the FRP, is soft compared to whatever material we are using here for the chuck, it is likely that as the load levels will increase, this material will cut through the FRPs and the failure will occur at the chuck itself or within the chuck. And this is a major challenge as far as testing of FRPs is concerned. So, designing these devices or these anchorages is a technological challenge as far as FRPs are concerned, their use in the field in the post-tensioned pre-stress construction is concerned. Now, if you look at the tensile strength test of CFRM, the way it is shown, if we take the stress strain curve, the load strain curve, then depending on whether the material is aramid or glass or carbon, the stress strain curves are quite different. Carbon fibers are comparatively stiffer. You would recall from the last discussion that we did have high modulus of elasticity carbon fibers and intermediate modulus of elasticity carbon fibers, and that is what makes the carbon fiber reinforced plastics stiffer than glass or aramid, which have more or less the same behavior. We must remember that the stress strain behavior or the load deformation behavior of the carbon reinforced plastic rod or the aramid fiber reinforced plastic rod would be different than this, because this actual stress strain behavior also depends on the volume fraction of the fiber and the epoxy or the matrix in combination with which that particular fiber volume has been used. Now, comparing it once again as far as steel is concerned, this is what it looks like. For carbon, the modulus of elasticity is about 1/3 that of steel, and the biggest difference is that we have a large fracture load, but we do not have any capacity in terms of deformations is concerned. The deformation is brittle, it does not allow us any warning. There are no large deformations possible, and that is something which we must keep in mind when we are designing structures using CFRM. And once again, This is a comparison of the carbon and the aramid glass compared to steel, and we can see that as far as aramid glass is concerned, they are again softer than carbon, and therefore, as far as steel is concerned, they become even more soft. Once again, if we plot the mechanical behavior of in terms of stress and strain of the fibers, we can divide the stress strain behavior of the composite into two stages, stage 1 and stage 2, which are separated by this value here, which is nothing but the value at which the matrix becomes non-linear. So long as the matrix is linear and the fiber is linear, then the behavior of the composite is also linear, determined by the equation that we have already derived. When the matrix becomes non-linear, the behavior of the composite also becomes non-linear, or at least it changes its slope, and it fails at the value which is governed by the failure value of the fiber. So, we can see that even though the matrix itself has some capacity to sustain load in terms of higher strains, the fibers do not have that capacity, and therefore, the behavior of the composite as far as the stress strain is concerned till failure, to a certain point in time, it is linear, governed by the matrix, and once the matrix cracks, it is governed by the failure is governed by the failure strain of the fibers. So, with this understanding, so this is a very important understanding as far as the stress strain behavior of fiber composites is concerned. This picture is just some data for tensile strength and modulus of elasticity of FRP bars, and I am skipping this because the data itself is not really important, because it depends on the volume of the fibers that are used, the matrix that is used, and so on. And now, let us try to look at some other tests which are relevant from the point of view of using CFRM as a reinforcing material in reinforced concrete or pre-stressed concrete. One of them is creep. Now, what is creep? Creep is the change in strain at a constant load. This picture shows the representation of a creep test using CFRM rods. What is done is that a CFRM rod is held in position at a constant load, that is, the load is held constant over a period of time. Now, depending on the load level, there will be a certain amount of deformation that is initially present in the CFRM, and that is the elastic deformation. As the load is sustained over the long period of time, successive fibers will one by one snap, that is, they will fail, and as the fibers fail, the other fibers will carry that load, because the load is not being changed over time. Now, what happens as a result of that is that the deformation over a period of time changes, as is shown here in the case of aramid fibers, and as one fiber fails after the other, the deformations suddenly change, and as more and more fibers continue to fail, there is a point where the deformation is reaching a level where the entire rod has basically failed. So, this is what is the basic creep behavior that is observed when we come to the CFRM. Because these fibers are independent units, so the behavior is quite different from that of steel, where we have basically a bulk material under sustained load. Then we have the concept of relaxation. Now, relaxation is the change in stress at a constant strain, and now depending upon the actual material, we may find that there is up to 15% of relaxation, and that relaxation again is represented as the change in stress values at a constant strain and is monitored over a long period of time. and we can see that carbon, aramid and glass all show certain amount of relaxation as far as changes in the stress values is concerned over a long period of time. Of course, 10 to the power of 7 is a very long time, considering that one day is just 24 hours. So, we know that in order to be able to carry out this test for so many days, it is not easy, and therefore, experimental data is very, very hard to come by as far as CFRM or any material is concerned. This is the representation of creep failure of CFRM, depending on whether the material used was carbon fibers or aramid or glass. So, we can see that the behavior of carbon fibers is much better than aramid or glass, which shows that all these fibers do not behave in exactly the same way as far as performance at higher load levels is concerned over a period of time. Now, coming to tensile fatigue. Tensile fatigue means the load is varied, of course, the weight is shown here, it is sinusoidal, it need not be sinusoidal, at a certain mean load level, in ensuring that all this region from here to here is still tensile. So, the material is not being unloaded completely, and within a certain band the material is being tested as, and the load is being varied over a period of time, and the variation could be in terms of the mean load being applied in relation to the failure load, or the amplitude of the load being varied, or the frequency of the variation, and so on. So, in a nutshell, the load is time dependent as against creep when the load is held constant. So, in tensile fatigue, the load is always in the tensile region, the material is always in tension, except that the level of tension varies depending on the amplitude and the frequency of the load application, and this load is applied over a long period of time. So, there is a loading cycle and we apply cycles of load. Now, this is represented traditionally in the form of an SN curve, which really shows that the number of cycles to failure at a certain stress level. So, this level here on the y axis is the applied stress to the failure stress. So, if we are going higher up in this picture here, we are moving in a manner where the applied load level is closer to the failure stress, whereas the stress here is lower than the failure stress. Basically, this level here, how high or how low is this level compared to the failure level. If this is the stress strain curve of the material and the applied load is being varied at this point versus the applied load is varying at this point, this here is at a lower stress level and this is at a higher stress level, and that is what is represented by these 2 points here along the y axis. And naturally, if the stress levels are lower, the number of cycles to failure are higher, and if the stress levels are high, the number of cycles to failure is low. And if we study this SN curve for the different fibers, we find that the glass fibers are most vulnerable as far as fatigue loading is concerned. Comparatively, the carbon fibers show much better performance. Now, coming to the deterioration of fibers or deterioration of the CFRM. This really consists of the deterioration of the matrix or the deterioration of the fiber. Looking at another way, what is the mechanism of deterioration, whether it is ultraviolet rays or we are talking of alkali. Coming to alkali attack, we see that if we immerse the CFRM in an alkali solution, and why alkali? Because we are expecting that the concrete is alkaline, we know that the concrete is alkaline, and the fibers or the CFRM is in contact with the high alkaline solution, that we talked about last time. And if we look at the change in strength with immersion time in the pH or a high pH environment, we find that glass is particularly vulnerable as far as its durability in high alkaline environment is concerned. As far as the model is concerned, we can look at it the way it is shown here, that there is a deteriorated skin portion that can be identified as far as a glass FRP is concerned, and only the core remains unreacted or undamaged. One of the ways therefore to use glass reinforced fiber plastics in concrete construction would be to have a coating on the glass fibers and the CFRM in order to protect them from the action of alkalis in the environment. As far as ultraviolet radiation is concerned, we have to account for, of course, the deterioration in the matrix and the fiber, and what most experiments or the studies have found that the deterioration in the matrix, of course, will be the same, but only for aramid fibers there has been some reported deterioration as far as behavior as far as the change in strength on account of the exposure to ultraviolet rays is concerned. Now, continuing again from the last discussion, let us look at some more field applications of CFRM. Here we are using CFRM in a tunnel construction. So, we can see that there is a net which has been placed using these bolts to hold a lining which is going to be applied on the tunnel. Similarly, here we are looking at FRP reinforcement being placed, which again is a grid as shown here for the reinforcement in a concrete wall. In this case, we are using FRP as cables. These cables are FRP cables in a cable stayed bridge. Another example is shown here, where we are trying to use FRP in the reinforcement of slabs in the airport apron area. This is another application of FRP, where its non-magnetic properties are being used in a parking lot, because there are some devices embedded in the slabs which will help detect the presence of a car when it is parked. And if there is a normal steel reinforcement, that may not be possible, and therefore, FRP may be used in at least certain places where those sensors are placed. This structure here shows FRP on a monorail structure. This picture shows the fiber reinforced plastics being used as a reinforcement in a small bridge in a golf course. Yet another example of using FRPs in concrete construction or civil engineering construction is in strengthening slopes using pre-stressed FRP tendons, as is shown here. This is another interesting example of using FRP as external reinforcement in the repair of RC bridges or reinforced concrete bridges. Let me explain what external reinforcement in repair work is. When we have a beam and it deteriorates, if there is a concrete beam with reinforcement which has cracked, one of the ways of repairing this beam with external reinforcement would be to just have something outside this beam and tie the two ends using something like a fiber reinforced plastic rod, and if we introduce tension, that is, we introduce tension in the FRP rod which is being used external to the beam, then what we ensure is that we have then we ensure compression on the concrete. That is, we are externally compressing the concrete, and this helps in closing the cracks, getting rid of additional deflections and so on. So, that is the principle of external reinforcement in repair works of RC bridges, and given their high strength, FRPs are a good candidate for use in this condition. This picture here is that of FRP as reinforcement in highway construction. This is another example where CFRM sheets have been used for strengthening of RC columns. So, we can see that as far as the concrete here, this is concrete. We can see that the concrete here in the column has now been wrapped using these FRP sheets. Now, how this helps as far as strengthening is concerned is by the following action. If this is a concrete column which is under the action of compressive loads, what happens with the column is that this concrete, when it is under compression, would tend to expand. Now, if we are able to wrap this concrete, which is something like this in the front view, then this tendency to expand is arrested, because in order that this concrete be now able to expand, this has to cause failure of this fiber sheets. Effectively, as far as the fiber sheets is concerned, for them they are under the action of radial expansion, and the sheets themselves, depending on how many layers of these sheets is there, all these sheets have to be all these sheets are subjected to tension. And in order that the concrete fail, it is important that all these sheets fail. So, this is one of the methods where FRP sheets are used in several layers wrapped around concrete columns to increase the load carrying capacity of the deteriorated reinforced concrete column. Schematically, the process is shown here, where the existing reinforced concrete column is wrapped using FRP sheets which are bonded using a resin or a matrix. So, in this case, the FRP rod is not manufactured at something like an FRP rod is not manufactured in the plant, but we get a composite made of FRP sheets and the matrix applied at site. Of course, at the end we could apply surface protection as far as matrix is concerned, in order to protect the matrix as well as the fibers from external influences such as water or air and so on. Similarly, we can use FRP sheets for strengthening beam slab constructions, and depending on what we want, we could use any of the configurations shown here. This is a picture of strengthening of beams using FRP sheets, and in this case as well, the FRP sheets are applied in certain layers or a certain number of layers which have to be designed, and these layers are held in position using appropriate matrix material, and these fabrics are reinforced in both directions. It is not unidirectional material in that sense. Continuing with the examples, we have CFRM with epoxy coated bars in the case of girders, which is shown here in this case, as well as in a pre-stressed precast concrete element as being shown here. There is no reason that as far as the application of CFRM in reinforced concrete construction is concerned, it should be remembered that these cannot be bent or treated at site, and therefore, all bent CFRM and the stirrups need to be manufactured in the plant and then brought to site. And there is no reason why CFRM cannot be used with traditional reinforcement or epoxy coated bars and so on in RC members or pre-stressed concrete members. And given their high strength, the CFRM are an ideal material for use in pre-stressed concrete as is shown here. So, this tendon here, which is going to be used for pre-stressing, could be a CFRM, and the other reinforcement be simple epoxy coated bars or normal bars, whatever we want. Coming to the close of the discussion today, let me once again acknowledge all the help and the material which I am using from the JSCE and my friends and colleagues, Professor Omoto, Kato and Dr. Bajpayee of the Department of Civil Engineering at IIT Kanpur, who have kindly allowed me to modify and use some of their slides, and from the publication in the ASCE. Now, at the end, this is some of the references that one may use in order to learn more about fiber reinforced plastics and their use in civil engineering. And before we close, some of the things which one could do a little bit more of study and thought. We could derive equations relating the load sharing, modulus of elasticity, critical fiber volume, shear modulus and so on for CFRM as a function of the properties of the matrix in the fibers. Some small derivations were shown in the discussion today for longitudinal loading, but a lot more can be derived if we use the same principles and try to understand the shear modulus of a composite material or the behavior as far as the transverse loading is concerned. We may try to answer the question as to why are fibrous materials stronger than bulk materials. We could study the test methods for the test of CFRM which has been discussed. We talked about the creep test, we talked about durability tests, we talked about fatigue tests, and it is important to understand what exactly is the nature of the tests which need to be carried out. We can study the design and fabrication of the ends or the chucks that hold the specimen in a tensile or a tensile fatigue or a creep test, so that we better understand the kind of discussion that we had as far as the importance of holding the specimen together or holding the specimen in place while carrying out loads or while applying the loads on the specimen is concerned. This is important because the stress levels are much higher than that of steel, and therefore, it is important that the chucks are designed and fabricated in an appropriate manner. With this, we come to an end for the discussion today. Thank you.